Alright, welcome back to the next concept, and that next concept is recurrence relations. So just as a preface, right, for every single thing that we are going to discuss from here onwards, it's not specific to AP, neither is it specific to GP. So this concept that we're going to be discussing from here onwards is really applicable to any single sequence or series. Okay, so I'm just going to write here. It's not specific to AP or GP. In other words, it can apply to any type of sequence or series. Alright, so just want to disclaim it because, up until now, we have been doing a lot of AP-GP for the past few videos. Alright, so what exactly is recurrence relations? So I'm going to be using a very simple example to explain to you this concept. Let's say I ask you a question. So I'm just going to write example here. I ask you, how much money do you have? Okay, so let's say that's the question I ask you. Now, let's assume that every day you save another $10. Okay, so on day N, right? Let's say on day 1, the amount of money you save is originally $10. On day 2, the amount of money that you save would be day 1's money plus $10, right? Now on day 3, the amount of money you save would be the amount of money that you save on day 2 plus another $10, right? And then same thing, right? When you go to day 4, it'll be the amount of money that you have on day 3, then you plus another $10, right? And then, this one could hypothetically keep going on and on and on and on. And on day N, the amount of money that you would have saved will be the amount of money that you would have saved on day N minus 1 plus $10. So realize that day N plus 1 itself is also a formula. And how do we compute day N minus 1? The amount of money that we save on day N minus 1 is essentially day N minus 2, right? Plus $10. Then, of course, here the $10 is here, right? Then realize that day N minus 2 can also be written as day N minus 3, right? And plus another $10 here. Then, of course, originally here we have plus $10 over here. And then originally over here we have another $10 here, right? And then this whole entire pattern could go on and on and on and on. But what it is that we realize over here is actually this concept called recurrence, or some people might say that this is called recursion. Okay, so I'm just going to write here the word. This is a concept of recursion. And why is this a recursive concept? It's because you realize that the same formula keeps recurring, right? And the same formula, which is day N equals to day N minus 1 plus 10, is being called upon within itself. So you see that this formula here is also the same formula that is used to compute this, right? Which is this. And within this itself, the same formula is used to compute this, which is this, right? And then this could hypothetically go all the way until it reaches back day 1, right? Where by day 1, you realize that day 1 is what we call the base case. So day 1 is called the base case. And why is it called the base case? Because the recursion stops here, right? So this is the concept of recursion or recurrence relations, is that each term is related to the next term by the same formula. And this one formula, it always links the two terms together, the next term and the current term together, right? This is just a very simplistic way of explaining, this concept. But I'm going to give you another example right now to maybe you might understand this second example a little bit better. Okay, so let's talk about this concept of factorial. So example 2, okay, factorial. Now, we know that the concept of factorial, n factorial, is n times n minus 1 times n minus 2 times all the way until times 3 times 2 times 1, right, until you reach 1. So for instance, let's say 5 factorial is 5 times 4 times 3 times 2 times 1, right? So this is just an example. But do you realize that this over here can be written as 4 factorial as well? So technically we could say that 5 factorial can be written as 5 times 4 factorial, right? And within 4 factorial itself, do you realize that 4 factorial can be written as 4 times 3 factorial? Because 4 factorial is basically 4 times 3 times 2 times 1, which is essentially 4 times 3 factorial, right? And then do you realize that 3 factorial itself can be written as 3 times 2 factorial? Because 3 factorial is just 3 times 2 times 1. Because then you see that 3, it can be written as 3 times 2 factorial, right? And then from 2 factorial, you realize that it's just 2 times 1, whereby 1 over here is the base case, right? Because 1 factorial is essentially 1, right? It breaks the pattern. So over here, factorial is also another recurrence relation. We want to write out the concept of factorial in a recurrence relation. It will be n factorial equals to n times n minus 1 factorial, right? And then you realize that n minus 1 factorial, the formula for this is n minus 1 is equals to n minus 1 times n minus 2 factorial over here. And then you realize that n minus 2 factorial is essentially just n minus 2 equals to n minus 2 times n minus 3 factorial. And then you realize that n minus 3 factorial, it calls on the same pattern again and again and again and again. So this is why we call these recurrence relations. It's because the relationship, or in other words, aka the function, right? The function that we use, it keeps on repeating. The function calls the function on itself. So this is just 2 very classic examples of recurrence relations. To summarize what I've just mentioned, recurrence relations all comes back to this concept called recursion. And what recursion is basically is you have a function, and in order for you to compute the value of a specific term, you will require the value of the term that comes beforehand. And in order to calculate the value of the term that comes before, you will use the same function on that term. So every term depends on each other, right? You realize that from the base case, as you keep moving forward, the next case depends on the before case. And the following case depends on the next case. And in order to compute the next case, you keep calling the same function again and again and again and again, right? So this is basically what recursion is. So if this is basically the concept, and there's not much formulas to this. It's more so of being able to manipulate this on your GC, which I will show you in a bit, right? So for the A-level syllabus, all you need to do for this portion is to really understand the concept. And I'm going to be using an example question over here to drive home this concept. So feel free to pause this video right now if you want to attempt this question. If not, I will jump right into doing this question and show you exactly how it's being done. Okay, so we are given a sequence, and the sequence is not specified whether it is AP or GP, right? So this one is not specified as AP or GP, right? And it's true, right? Because we can't tell whether it's AP or GP. So from here, we are given that U1 equals to A, right? This is our base case. Base case is essentially where everything starts from. And then you see that this one over here is our recursive relation, right? UR plus 1 equals to UR plus 5, where R is bigger than or equals to 1. So if I can write this out in a simple table for you, U1, U2, U3. U1 has a value of A. And then you realize that U2 is essentially, based on this formula over here, is 3 of U1 plus 5, right? So U2 depends on U1. And the value of U1 is A. So U2 is essentially 3A plus 5, right? And then for U3, using the same formula over here, the same recursive relation, you realize that U3 is 3 of U2 plus 5. So U3 depends on U2, right? That's what I've been always saying. And the value of U2 is what we compute over here, which was computed from U1. So you see that every term depends on the term before. So this over here is essentially 3 of 3A plus 5 plus 5. Eventually that gives us 9A plus 20. So this is the answers to A, right? It's just showing you how recursion actually works. And this question was pulled directly from the 2025 A-level H2 math paper. So you can see that the questions are not really hard, given the fact that I used the A-level question as an introduction question for you, right? But I hope that you are able to see the idea of recursion inside of this question. So now it is given that 4, summation of 4, so summation of R equals to 1, UR equals to 110. Now, I have not discussed the concept of summation or sigma notation yet, which is something that I'll be going through in the next video. So for this part B over here, you might want to pause this video first and go and watch the next concept, then come back to this. Right, but just for the sake of wrapping up this question, I will do this question for part B right now. So for part B, how this is being read is the sum of the values from R equals to 1 to R equals to 4. So we can view this as U1 plus U2 plus U3 plus U4 equals to 110. And we know that the value of U1, U2, U3. So what's left is just finding out the value of U4, right? And using this idea above, U4 is essentially 3 times of U3 plus 5. So U4 depends on U3. And what's the value of U3? The value of U3 is what we computed earlier on, which is 9a plus 20. So the value of U4, right, would be 3 of 9a plus 20 plus 5. So in the end, we get 27a plus 65. So you see that U4 depends on U3, U3 depends on U2, U2 depends on U1, and U1 does not depend on anything, and that's why we call it the base case. So from here, we just sub everything in. So a plus 3a plus 5 plus 9a plus 20 plus 27a plus 65 gives me 110. So I combine everything. I end up with 40a plus 90 gives me 110. 40a gives me 20. A equals to 20 divided by 40, and that gives me a value of half over here. Right? So this is the answers to this question over here. Understand that I have not formally gone through this symbol yet, which I will be doing in the next video, but if you already learned this concept, then this sigma notation portion shouldn't be too difficult for you. Right? So let me know if you got any other questions in the comments below. If not, I'll see you in the next video where we'll go through the next concept, which is sigma notation. And I'll see you there.